Hello and welcome to another video. In this video we're going to be working on 2 sum is less than k, and it's very similar to the original 2 sum except for instead of finding two numbers that add up to a target, now you're asking for give me the biggest sum that I can use making two numbers that's less than this k that they provide. So in this first example it is 34 and 24, which is right here, and it will give you sum 58. In the second example you can't get any two numbers that gives you a sum less than 15, because anything will give you bigger. So there's a few ways of doing this, and what you're really going to want to do, the original 2 sum used a cache to get an exact number, but we don't want an exact number. We want to get the biggest number possible. So we're going to use something else. So what we're going to do is, now obviously you can just have like an n-squared solution, but the way this is going to work is if you're looking for like the biggest number possible, it's going to be very convenient to sort our numbers, and then we can look for solutions that we can use. So we're going to sort this over here. And now there's two ways of doing this. That one is pretty obvious, and the other one is not too difficult either, and they're both the same time complexity. So for the first one, we can just go through every single number. So if you think about it, the brute force solution would go through every single number, and then it would like manually search through everything here and look to find the biggest sum possible. But if we know that our sum needs to be less than 60, that means our biggest sum can be 59, let's say. That means that if we use the 1, our second biggest number has to be 58 or less. So we could do a linear search, but because this is already sorted, we can just binary search for the second number. So we can binary search for the biggest number we can find, which will be 54. And then our sum will be 55. Right? So we can binary search, which would bring down our time complexity from n squared to n log n, because for every number you would binary search. Then for 8, we're going to look for the biggest number we can find. And you can also, I guess if you wanted to, like do it in like a smart way, you can bring down your constraints as well. And this is kind of give you the intuition for the other problem. So if you see like for 1, it's 54. So for 8, it can't be anything bigger than 54. So you can just start with like your right side being what your first one was, right? So for initially, when we do 1, we could say like, okay, well, we want to search through the whole array. But then for 8, we don't need to search through the whole array. It's never going to be anywhere over here because we increased our left number, so the right number can't be bigger. So for 8, we could search through anywhere through here. So the biggest number is going to be this number here, and we're going to get 42. Then the same thing for, and 42 is worse than 55, so we'll keep 55. Then for 23, we can say the same thing. We don't need to search through any of this because we increase our left number, so our right number has to be at least this. So if we add these together, then we will get 57, which is better. And then for 24, same thing. It can't be anywhere over here. So we'll try this area here. And so our best number is 34. So we'll get 58. So hopefully you're seeing the intuition for the second way to do this. And then for 33, remember it can't be anywhere here. So we would only have to search this number here, and we didn't find anything. And that's fine because you don't really need a number. Like if there's nothing bigger than the number, that means you might have already used this number before, and so you're basically done. So we can basically write down like for each number, our right has to be less than or equal to previous array, right? Like for the 1, we search through the whole array. But then for the 8, we know like for the 1, this was our number. So then our right can be this. Like our bounds can just be this section. And then because for the 8, we use this number, that means for the 23, we'd have to use this and so on. So this is the other intuition for the problem. So let's actually go back and get rid of this. And we're going to show the other intuition. So the other intuition, now that we know that we can reduce our constraints every time, is just going to be a 2-pointer again. And the way it's going to work is we can just check for what's our sum. And if our sum is too small, we'll increase it. And if our sum is too big, we'll decrease. And we'll just record all valid sums and then our best sum. So let's take a look at that. So we're looking for 59 or better. Or 59 is like our best possible sum. So if we get 59, we can just return. I guess that would be another way to do it. Like if you get k minus 1, just return right there because that's the best solution. So that's slight optimization, but not too big of a deal. So here our sum is 76. So it's too big. So if it's too big, we need to move down our right side, right? So let's actually learn how to use this program for once by doing this. And then we can make a another one of these, and like this. Now we can actually move these arrows instead of deleting 500,000 times. Okay. So our sum is too big, so we need to make it smaller. So now we have a valid sum, which is 55. And now if we have a valid sum, we need to see if we can get a bigger sum, right? Because we're looking for the biggest sum possible. So we're going to look for this sum. This is too big, so we're going to reduce it. So this is valid, but it's smaller than what we had before. So we're going to try to increase it. This is better, so 57. Now we're going to try to increase it again. So this is obviously better as well. So we get 58. And we're going to try to increase it again. And this is too big. And then finally, when we try to decrease, we will have our left meet our right. And they can't be on the same number, right? So you do this until your numbers overlap. So essentially, if your sum is too big, you make it smaller. If your sum is good, you record it, and then you make it bigger. So it's kind of like just a greedy two-pointer. And you can see that from the binary search, your constraints keep decreasing and decreasing and decreasing. So you don't actually need to binary search. You can basically just sort and do a one-pass solution until your pointers meet. And yeah, so now we can code it up. So we can say left equals 0, right equals length nums minus 1. We want to sort our numbers. And finally, we'll have a result. And what we can do is we can just set the result equal to -1 and we try to maximize. And if there is no valid sum ever, we'll just return -1, which is what the problem was. So we can say while left is less than right, we can get a total value, which is nums left plus nums right. And then if total is less than k, we have valid sum. So we will say result equals max result total. And we will try to increase our total by moving the left up. Yeah. And if not, then our total is too big, so we need to decrease the right. Then we just loop through this until the pointers hit, and then we can just return our biggest number that we found. So we can return there. Let's see. Right equals. Oh, yeah, I need a 0. Actually, I need this. There we go. Okay. Now, hopefully, there we go. And yeah, so pretty efficient solution. This is basically n log n as good as you can do. So binary search will also be n log n, but in practice it will be slower because you're actually doing n log n for every single time. So yeah, you're basically doing like an n log n plus n log n, and the other one is n log n plus n. So this is as good as it gets, I think, for this one. And for the complexity here, so we did a sort, which is n log n. And then we also don't use any space. We just use left and right with a two-pointer. So yeah, hopefully this was helpful. Definitely a kind of cool problem. Haven't seen it before, so definitely kind of interesting. And yeah, if this was helpful, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.